Okay, now let's talk about transport by filtration across a membrane. So in the last two lectures, we talked about one coefficient we call the actual sieving coefficient, SA. And at that time, we defined it as MA dot divided by CA. CA is the concentration on the feed side multiplied by Q. This is the same as since MA is the field concentration inside of the membrane, the average concentration like CA filtrate. So this ratio actually gives us CA filtrate divided by CA surface. So this surface referred to this is a membrane. And the concentration on the surface of the membrane instead of like a bulk away. This is what we call the actual sieving coefficient. And later on, and we will use more likely the definition, which is the CA filtrate divided by the CA surface. So the filtrate would be like the concentration in the membrane. So this is the filtrate. We also had an equation for CA, for SA, which is 1 minus lambda squared multiplied by 2 minus 1 minus lambda squared. You had it in your notes earlier, so I'm just put it in the perspective, in the context of what we were discussing in the past. So if you have a slow filtration, if your Q, so you have a Q, if your Q rate is, well, the Q is everywhere. If your Q rate is small, or if the membrane is very permeable to the solute, then solute would easily go through the membrane. Then that should not be an issue. However, sometimes when you have high filtration rates, then you may not have a very good like distribution of solutes. So I mean on the high Q. So here are solutes everywhere. If your Q is so large, then the flow tend to push all the solids quickly to the membrane. However, membrane doesn't have enough permeability or doesn't allow that fast convection to go through the membrane. Then you would have concentration to be accumulated on the surface of the membrane. So this is called concentration polarization. On the high Q, we would have a layer of retained solutes built up. So a layer of retained solutes built up near the surface where the feed side of the membrane. So, and this phenomenon is called concentration polarization. We call it concentration polarization. Or you can think about there is a layer like we call it like concentration boundary layer thickness delta. Here you have a um, highly concentrated solid compared to the bulk. And in this case, the solid concentration on the surface, so this is the surface, is not the same as the concentration in the bulk. So then we start to define another sieving coefficient we call observed. Observed sieving coefficient we call the SO. SO is the ratio of Ca at the filtrate divided by the concentration in the bulk. So we call it observed because usually if you are like doing an experiment or considering what happened in some biomedical devices, it's hard for you to actually get what is exactly on the surface of a small membrane, especially if you have very small membrane and you cannot get to that area. Or maybe in some scenario, it's harder to measure. But what you can get, what you can easily observe is the concentration in the bulk part. So if you know observe the sieving coefficient, then you don't need to calculate what happens, or you don't need to measure what happens on the surface. You just need to know what's happened on the bulk, and then you can relate to this or do some calculation to figure out what is the filtration rate, Ca concentration in the filtrate and the mass transport rate, etc. So we want to know the relation. So we want to so to do this, let's figure out what's the concentration. So let's say the concentration profile within the layer is Ca. Let's put Y. Let's figure out how it's distributed. So let's develop a coordinate Y so that it starts from the surface of the like a membrane. So it's points towards the bulk part on the feeder side. And then we can draw a control volume. Let me just draw a control volume. You can make it very long so that the surface area doesn't matter. Or you can just call the surface area S. So the control volume, now because it's so thin, you can assume that the concentration within the control volume is just the same as everywhere. So you may think about, or you can collect the terms. On the steady state, because of the filtrate, you would have a transfer of a mass transfer into the control volume from the left-hand side. This is due to the filtration. So into the control volume, you have Q multiplied by Ca. This is from the left surface. The volume. And you can also think about what's leaving out of the control volume. It can leave in two ways. I think it's better to draw maybe let's draw the control volume here in this way. Maybe that's better. So you have one side is anywhere in Y, and another side is like attached to the membrane. So you can have flux out of the membrane into out of the membrane, out of the control volume. So on the left-hand side, you have diffusion, because if you have a concentration polarization, you have highly concentrated close to the membrane and then low concentration in the bulk, then there will be a diffusion process. So the out would be on diffusion would be minus D naught. D naught is the diffusion coefficient in a solvent. In this case, it may not necessarily be water. You can think of it may be a plasma. Then in this case, D naught would be the diffusion coefficient of solid in the plasma. So this D naught means whatever the physiological consideration we are consider, this is the diffusion coefficient in that medium. And S is the area, and then you get dCA, the function of y dy. This is Darcy's sixth first law. So this is out of the control volume from the left surface of the control volume. You can also have solute. You also have solute leading from the right side of the control volume. This is due to the flux across the membrane, the filtration. So you will have Q multiplied by Ca filtrate. It is the right surface. So on the mass balance, in equals to out. So you have Q Ca as a function of y equals to minus B naught plus Ca y y to Ca filtrate. Now what you can do is you can rewrite these terms. So you just organize this equation. You organize the goal of organizing this equation is to separate the variables. Separate Ca and the y to the two sides of the equation. So what you would get is Q dy equals minus B naught dCA. Ca as a function of the y minus Ca filtrate. The Ca filtrate is considered as a constant. But the C itself is a variable. Here Q, we define it as capital Q divided by the area. So this is flux per unit area. Now the next you integrate over the boundary layer thickness. You integrate. So on the left hand side you have Q integrated from 0 to delta C dy equals to minus d naught. Now the concentration on the surface, because you need to see what happens at y equal to 0. The y equal to 0 is the CA surface. Then at y equal to delta C, it's a CA bulk. Then you have DCA. CA minus. And just integrate it. Integration, you find a Q. Of divided by delta C. Natural logs CA bulk divided by CA surface and CA filtered. Now we have B naught divided by Q. Let's define. Actually, if you recall what we discussed earlier, if you have a diffusion coefficient divided by some thickness, you know that this is mass transfer coefficient. So this is the mass transfer coefficient over the boundary layer. So we can rewrite our Q equals to minus AM multiplied by log CA bulk minus CA filtered divided by CA surface. Subtract the CA filtered. And after some algebraic manipulation, LGE is manipulation. We will relate observe the sieving coefficient with the actual sieving coefficient. So you have SO expressed as a function of SA. So minus Q divided by Kn. Okay, so this is I'm leaving an exercise. This is exercise. So derive the middle steps. or complete the middle steps. So this is your homework. Now we have this, we can see some interesting limits, like to develop some physical intuition based on this equation. So when Q divided by M, the terms in the exponent goes to 0. It corresponds to low filtration flow relative to diffusive back transport. So it's a low filtration flow relative to diffusive back transport. In this case, the relative diffusive back transport dominates. That means the solute in the polarized layer tends to move the solutes back, and that's what leads to, like, on the feed side, the bulk part and the surface would be more or less similar. So this would lead to the observed sieving coefficient approaches the actual sieving coefficient. On the other hand, when Q divided by Km is much larger than 1, it means strong filtration flow with limited diffusion. Strong filtration flow with limited diffusion. Then we have observed the sieving coefficient close to 1. What it means is that the solute concentration in the filtrate is essentially the same as that in the bulk. So solute concentration in the filtrate is essentially the same as that in the bulk. So these are the two limits when you compare Q versus Km, and each one corresponding to some physical interpretation of the process. Now let's also briefly mention what we call the estimation of mass transfer coefficient in stirred ultrafiltration cells. Suppose let's consider a scenario. So this will be a way to estimate like the K, if you want to like estimate the mass transfer coefficient. So let's see how I'm going to draw this. So suppose you have like this, you call it a cell, and then there's a membrane. You want to like filtrate something. This is a membrane. Maybe let me take another there are holes on the membrane. Maybe that's a better way to see it. So there are solutes. We want to transport it across the membrane. And then you may stir it, which is called a stirred ultrafiltration filtration cell. You stir the fluid, and the stir will give rise to some angular stirring speed. So omega. Stirring speed. And the radius of this device we call R cell. And then the Reynolds number for this case is Reynolds number would be rho is the density of the fluid omega R cell squared divided by mu. Mu is the dynamic viscosity of the fluid. Recall that the velocity is omega r. So usually in the Reynolds number, you have rho multiplied by velocity multiplied by a length scale. And the velocity is omega r and the length scale is r. That's what gives you omega r squared. And the Schmidt number is mu divided by rho BAB. So now you can have someone propose a Schmidt number in the stirring flow as this Schmidt number is 0.23 Reynolds number to the power of 0.567, and then to the Schmidt number to the 0.33. Now you may wonder, why do we care about this Schroeder number? Because Schroeder number is related to the convection across a boundary layer. So if you have like a boundary layer, I also draw this. Let me just draw a lot of dots here. If you have a boundary layer of solutes, and then if the mass transfer coefficient of the boundary layer is Km, then the Schroeder number relates to Km by this equation we discussed in an earlier lecture. If you forgot that, you can recall, you can review that. So it's Km mass transfer coefficient multiplied by the radius of the cell divided by the diffusion coefficient. So this is also a convection, surface convection divided by diffusion. This is the ratio of these two. So if you know the Schroeder number, and then you can get a Km. Sometimes Km is practically helpful. And this is one reason people study this type of problems. And and also, if you know Km, then you can get Q divided by Km. Then you can relate S observed this way. So you can do a lot of things if you know the Kn. Let's look at the example. So this is our example. A solute with a molecular weight is being filtered, given you molecular weight, is filtered into at a temperature through a microporous membrane within a stirred ultrafiltration cell of diameter 13 millimeter. The viscosity of the solution is given. This 1.002 CP center poise is the viscosity of water at 20 degrees C. The diffusion coefficient of the solute in solution at this temperature, okay, it also give you what we call the BAB. The membrane has a nominal molecular weight cut off. This means if you see this terminology, it means the size of the membrane hole or pore is of the size that is corresponding to a molecular weight of 80,000 grams per mole. So if you have molecule which is heavier or larger than this one, it cannot go through the pores. They give you the Stirling speed, also give you the filtration flux rate Q. Ask you to estimate the observed sieving coefficient. So you may think about why they give us molecular weight. This is because you can relate a molecular weight to the size. So recall when we did the Stokes-Einstein relation, we had saying, okay, if you know molecular weight, you can know the radius by using this equation. 3 multiplied by molecular weight divided by 4 pi rho Na to the power of 1/3. Here rho we are going to use just the density of water. 1 gram per centimeter cube is the same as 1,000 kilograms per meter cube. And this Na is Avogadro's constant. So that means we can figure out the radius on the pore radius and the solute radius. So to find the pore radius, use molecular weight equals to 80,000 grams per mole. And you get R equals to 3.16 nanometer. And the solute radius, we use molecular weight equals to 45,000 grams per mole. And you get A. We are using the same notation of the what we used when we introduced the lambda. So it's 2.61 nanometer. So from here we can know what is lambda. This is always in our context, it's the ratio of the radius of the solutes divided by the radius of the pore. And then in this case, it's 2.61 nanometer divided by 3.16 nanometer. It gives us 0.825. And then with this lambda, we can, first of all, we have no difficulty with calculating the actual sieving coefficient because we have a formula for that. Will we put a small number? Let's see. Okay. Now, in order to get the observed sieving number, we need to use this equation. In order to use this equation, we need to know Q. We are given Q, but we need to know Kn. But we don't know Kn, but however, we can figure out the Kn by using the Schur number. So that's where it comes in. In order to know Schur number, we need to calculate the Reynolds number and the Schmidt number. Rho omega R cell squared divided by mu. So let's see. Rho is 10 to the power of third kilogram per meter cube. Omega is angular velocity. So we have 8 revolution per minute, or 800 revolution per minute, with corresponding to multiplied by 2 pi divided by 60 a second. That's the angular velocity. The radius of the cell is 0.015 meter cube. The viscosity is 1.002. The points. Then if you convert it to Pascal, you have 10 times 10 to the minus 3 Pascal second. So the Reynolds number is 18812. Let's also figure out the Schmidt number. Mu divided by rho UAB. Mu is the same mu dynamic viscosity of the fluid. Rho is the density, same density as water. And the AB, the diffusion coefficient, it's given in the problem statement. Let's convert it to meters square per second. So we need to divide by 10 to the power 4. So we have 10 to the power of minus 11 meters square second. Then the Schmidt number is 0.03. Okay, let's find the Schur number. Schur number is 0.23. Reynolds number to the power of 0.567, and then the Schmidt number to the power of 1/3 to give us a number. Now we can figure out the Km. It is 1489 multiplied by 280, the diffusion coefficient. And then the radius of the cell. Well, I mean, the cell means the device, not that the tissue cells, like endothelial cells or red blood cells. Not that cell, but it's referred to the Stirling device. Sometimes we also call them cell. Give us a Km number, mass transfer coefficient. It's 6.2 times into the minus 4. Okay, now we can get the app or the observed sieving coefficient as a function of the actual civic coefficient and a function and related to Q and Km. Let's plug in a number. Minus Q. Q is given. 10 to the minus third centimeter per second divided by the Km, and then plus okay, it gives us a number. Hopefully this is correct. All right, so you see the procedure of how this is done. And this is an example that we learned multiple things from it. First of all, when people give you molecular weight, you should immediately flash in your mind, okay, that means I can know the size of the particle. That's a very handy tool. And also, whenever you want to relate the sieving, observe the sieving coefficient with the actual sieving coefficient, you need to think about, okay, I need the mass transfer coefficient. And how do I get it? So in early lectures, we have multiple lectures which also talked about the mass transfer coefficient. For some cases, we actually derived this. For example, we had a mass transfer coefficient for diffusion from an infinitely large plate or from a spherical surface. We had those derived. So you can for those scenarios, you can use the Pm mass transfer coefficient obtained from theoretical derivation. And this is in this the stirred like environment is another example that people give you an estimation of the mass transfer coefficient. So the mass transfer coefficient, it depends on the geometry, depends on the flow rate, depends on a lot of factors. And it's problem specific. So if you wanted to know how to relate to like sieving coefficient, then you need to figure out for that particular problem, how do you figure out the mass transfer coefficient? So this is what we learned from this example. And I suggest you go through this on your own just to clean up the logical flow in your mind on this type of problem.